a 10-point FRQ. We're going to do A and B of it in this video. This is a lab. As you can see, they're showing equipment in a balance that's good to 1,000th of a gram, and they're making some stuff. Here's the reaction. This is something we should focus on. We've got a metal reacting with iodine to make a compound, Mi2, probably an ionic compound. The stoichiometry is 1:1, so that's good. We don't have a complication about having to worry about changing moles. Let's read it. To determine the molar mass of an unknown metal, so we're going to find the molar mass of this metal, grams per mole. So we got to have grams and moles. A student reacts iodine with an excess of metal. Now, this is important. That means we've got more metal than we need. So its mass is going to be irrelevant right now in terms of how this reaction proceeds. Iodine is going to be our limiting reactant. The reaction proceeds until all the iodine is consumed. Okay, we use the iodine as the limiting reactant. The Mi aqueous solution is quantitatively collected and heated to remove the water, and the product is dried to a constant mass, so we get our Mi2 in the end. Let's see what our first question is. First question, here's the data. As you can see, we got everything to a milligram, and we're careful when we're doing lab experiments for significant digits. Given that the metal M is in excess, calculate the number of moles of iodine that reacted. Okay, here we have our data table, and we need to get this iodine. Here we've got the beaker and metal and iodine. Well, the difference between these two has got to be the iodine. Now, be careful with this subtraction, because let me get the calculator out and we'll do it. First of all, because there's a lot of numbers involved, I guess we could just go with, and forget the 12, but I'll do the whole set of numbers. 127.57. That's this weight. Then I'm subtract just the beaker and the metal. And minus 126.549, double check, 127, 126, enter. This has got to be the mass of our iodine. Let's look at this in terms of a subtraction, where we've got the two different things, have just the iodine left over, because when we subtract these two, it's the mass of the iodine. Usually on AP questions, writing off the 3 sig digs is fine, but this is a lab data, and they used an expensive balance to do this. I mean, a milligram is pretty accurate. So you got to remember to include this milligram in a subtraction. Subtractions and additions, we go by columns that we know the certainty of. So this would be the mass to the right number of significant figures, but they want the moles of iodine that react. We can just take the periodic table to find out the molar mass of the iodine. I can change a mass of any substance that I know the formula of into moles. Fortunately, we have a separate booklet for the FRQ where we have the periodic table that we can flip to while still having our booklet open. So let's do the calculation to change this grams into moles of iodine. Well, we know you take grams and divide it by the molar mass, but this is I2, so we're going to have to get the formula right and multiply it by 2. So I'll get the iodine 126.90 times 2 is I2. And I'll close my parentheses. I don't really have to on this calculator, but 1.021, that was our mass, grams, divided by our molar mass, grams per mole, and we'll get moles. There, that answer we'll be able to write on our answer sheet. We've got plenty of space to do that. So we're going to do this calculation, mass of iodine, and divide it by the molar mass of iodine, and our answer is 0.00402. Well, how many sig figs are we going to use on this? Well, we had 4 sig figs here for our mass. So we should show our moles to 4 sig digs also. Leading zeros don't count. 4023 moles of iodine. This looks like one of the questions where they would penalize you if you didn't use the right number of sig figs. First of all, you're using more sig figs than you normally would use. And we have 1 point for the number of moles, but you will need the right number of significant figures for this. So be a bit careful, especially with labs where you have an addition or a subtraction. So we've got a point already. Now, calculate the molar mass of the unknown metal. To get a molar mass of the metal, we're going to have the grams of the metal, but we had the metal in excess. So how are we going to find the mass of just the metal that reacted? Well, this is where we have this Mi2. We know the mass of the Mi2, and we know the mass of the I2 right here. So that'll let us get just the metal all by itself. We've got the mass of the Mi2, metal and the iodine, and we have the mass of just the iodine that we just did earlier. We've shown our work. Well, by the way, make sure, even with the subtraction, that you show your work on your answer. You want to show the subtraction written down. You don't have to write all the rest of the stuff, but you're going to have to show anything that you calculate. So include this answer. Remember I said many graders are so sad when they see correct answers, but they don't see the work done to get those answers. We'll do our subtraction, and we'll get our mass of metal. And probably we'd get a point just being clever enough to realize that we have to subtract the mass of the Mi2 from the I2. We can't use the beaker and the metal because the metal was in excess. We need to know the stuff that reacted. Now, if we have the mass of the metal, then to get the molar mass, we need the moles. This is where our previous answer comes in. We know the stoichiometry of this reaction, all the way to the top, sort of hidden away. 1 mole of I2 produces 1 mole of Mi2, so they're going to be the same. This is where they're checking to see if we know our stoichiometry, do our nice calculation, where we know we have our number of moles, and we know we have the mass of the metal, and we can figure out the molar mass. So I'm going to take my 0.263 grams and divide by my last answer. And there's our molar mass. Back to up here again. 65.4? 65.4. Oh, this looks nice. This reaffirms our answer that we probably have a zinc iodide. 65.4 grams per mole. You get 1 point just for the grams of this. That's pretty good. I mean, that's nice being able to do that subtraction. And then we'll get another point, I'm sure, for the molar mass. A total of 3 points out of this 10-point FRQ. I'm sure one of the common errors on this FRQ was where instead of using the mass of the M by this subtraction, that instead people took the lab data where they had the mass of the beaker in excess metal and the mass of the empty beaker and determined that the mass of metal was 1.092 grams. This wasn't only a small part. 0.263 grams of this metal actually reacted. Now, if you did the subtraction and said the mass of the metal was 1.92 grams, and of course you'd show your work, you wouldn't get the point for that. That would be an error. You'd miss a point on this FRQ. But if you then went and did the molar mass calculation, where you took the 1.092 grams and divided it by your molar mass that you found of the moles of M that you determined from iodine, you would get the point for this reaction. If you put down 271.4 grams per mole, but really you'd say, what? Something's wrong, because there's no element that weighs that much, and you'd say, but still, you did the setup right. You did the grams divided by the moles, and you'd get the point for the molar mass. So you get 2 out of these 3 points. The nice part about the FRQ grading is that you're not double penalized. If you knew how to figure out the molar mass because you had what you thought was the mass of metal, and divided by what you calculated the moles of the metal would be because of the stoichiometry of the reaction, you get this point. Remember, even if you flub up, sometimes you can save things in the end as long as you do your calculations correctly and consistently.